So in this video, we're going to take a closer look at the refraction, and specifically we're going to talk about something called Snell's Law. Now, Snell's Law doesn't deal with the change in speed and wavelength, what happens with the wavelength and the frequency and the speed. It deals more with the direction of the waves. What direction will the waves travel? Now, in order for us to think about Snell's Law, we have to learn about a new property called the index of refraction. Now, the index of refraction is just simply it's a ratio. It's a comparison of the speed of light in a vacuum. That's where light travels at its fastest. The speed of light in a vacuum. The symbol for that is c. That's not a variable. That's a constant. The letter c represents the speed of light, and it has a speed of 3.0 times 10 to the 8th meters per second, or 186,000 miles per second. 186,000 miles per second. The Earth is only 25,000 miles all the way around. So that means that at the speed of light, you would be able to travel 7.5 times around the Earth in 1 second. That is a mind-boggling speed. There is nothing else in the universe that travels faster than that. The speed of sound, just for example, in the air, the speed of sound is 0.2 miles per second. 0.2 miles per second, or approximately a little bit less than 1,000,000 times slower than light travels. So light travels at an incredible speed, but when light enters into a new medium, a medium in which there are atoms that it has to deal with, then it doesn't travel as fast. It slows down. So those atoms are sort of an obstruction to the light rays, and so the light slows down. Now, in the air, it doesn't slow down very much because air is not very dense. But things like water or glass, or let's say a diamond, those are much denser, and the light travels significantly slower in those. And the index of refraction is just a way of putting a number on how much slower is it going to go compared to the speed of light in a vacuum. So the formula for the index of refraction is N is equal to C over Vm. Okay, and these three variables, we're going to identify them each by name. So N is called the index of refraction. All substances that allow light to pass through them have something called the index of refraction, and we'll look at a couple of examples. C is the speed of light in a vacuum. Okay, and so in case you're not familiar with the idea of what a vacuum is a region of space in which there are no atoms. There are no solid things, there are no liquid things, and there is no air, there is no gas, there is nothing. It is completely empty space. That's what light likes. It likes to travel when there's nothing in its way. There is nothing obstructing its path. Now, as we just said a moment ago, the speed of light is 3.0 times 10 to the 8th, or 300 million meters per second, and that number will be given to you. Okay, that is a constant. It would be wise of you to memorize it, but it will be given to you on every test and every exam that you'll see. So you just really need to recognize that letter C is not a variable, N is a variable, V is a variable, but C, no, that's a constant. That is a constant value. And then lastly, we have Vm, and Vm is simply the speed of light in the medium. And by the medium, I mean whatever the light is traveling in. So if the light is traveling in, let's say, for example, let's say that light was traveling in a vacuum. Well, then the speed of the light would actually be just the regular speed of light. So I would end up with C divided by C, and I would find the index of refraction to be 1. So let me give you just a couple of common indexes of refraction, but these are things you can look up in the book, you can look them up on the internet. I mean, it's easy to find out these index of refraction. So let's say N vacuum. Okay, the index of refraction in a vacuum is 1 because it's going to be the speed of light in a vacuum divided by the speed of light in a vacuum. So it's not really too much going on there. It is 1 forever. It is a number which has an infinite number of sig figs. But in air, the index of refraction is very close. We are typically going to just say that it's 1 exactly, but it's actually 1.001, so it's very close to the index of refraction for a vacuum. Air is not very dense, and so it doesn't slow down the light very much, but it's certainly not it's not exactly the same as the speed of light in a vacuum. We can imagine n for water. In water, the index of refraction, it does depend on what's in the water, but typically the index of refraction is around 1.33. The index of refraction for glass can vary a lot. However, in general, it's going to be somewhere around 1.54, could be down to like 1.4 or something, or up to maybe like 1.6, depending on what kind of glass. There's all different types of glasses. So you can see the numbers are getting bigger. I'm getting to things that are more and more dense. You imagine if I put glass in water, it would sink because it's more dense than the water. And so the index of refraction is increasing. The highest index of refraction that I am aware of is for a diamond. And that index of refraction is 2.44. So the light slows down tremendously when it gets into a diamond, and that is part of why diamonds do what they do. And we'll look at this a little bit more closely. We'll touch back briefly again on the diamond at the very end of this video as to what does that high index of refraction, like why is that so important? Why is that something that a diamond, part of the properties that diamonds exhibit is because they have such a high index of refraction. And of course, diamonds look their best when there's lots of light shining on them. And so we'll come back to that in just a moment. But before we do that, let's use this index of refraction for glass to figure out what is the speed of light in glass. So we're simply using the index of refraction of glass of 1.54. We know the speed of light, which will always be given to you, is 3 times 10 to the 8th meters per second. And what we're looking for is the velocity or the speed of light in glass. Now the formula says that n is equal to c over vm, and the reason why I chose to do this particular example is this is probably the hardest one algebraically. If I had given you the speed in the new medium, then you could easily calculate it. You just plug it in. I would take 3 times 10 to the 8th and divide it by the speed, and then I would get the index of refraction. And the index of refraction is always a number that goes between 1. 1 is the lowest value for the index of refraction, and then it goes up to, in theory, it goes up infinitely. But as I said, the highest index of refraction that I've ever seen personally is 2.44. There may be some that are a little bit higher, but the diamond is one of the highest indexes of refraction that I am aware of. So because the thing we're looking for is down here in the bottom of the fraction, that's what makes this a little bit more challenging. So my first step is going to be, I'm going to multiply the left and the right side by the velocity in the new medium. So that would give me Vm times n is equal to c. Then to get Vm by itself, I would just divide by n, so I end up with c over n. And now I'm ready to go ahead and plug in the numbers. That is 3.0 times 10 to the 8th. Make sure to use the scientific notation feature of your calculator. And then n, as we just saw, was 1.54. And when you plug that into your calculator, if you do it correctly, you should see that the speed of light in glass is about 1.95 times 10 to the 8th meters per second. Okay, and this is something you may be asked to do to calculate the index of refraction or to calculate the velocity. There's only 2 variables in this equation, the index of refraction and v. This is a constant. It's not something that you need to solve for. It is an established number that we know very well. We've measured it very, very accurately. That number will never change, but these 2 numbers, you'll be given one and you'll be asked to solve for the other one. Okay, so now that we have a little bit of an understanding of what the index of refraction is, let's see the index of refraction in action, in a problem where you would actually need to use it. So let's move this out of the way and let's come back to this question of how do you apply the index of refraction to this thing called Snell's Law. So Snell's Law deals with the situation where a wave, can be any wave, but we're going to be really particularly focused on light, a ray of light. Now I'm going to have a surface that is, in this case, a fast medium, and it's going to transition. The wave is going to go from the fast medium, it's going to travel downward like this, it's going to strike the new surface, and it's going to be transmitted into the new surface, and so as a result, there's going to be some refraction. Some things are going to change. The speed's going to slow down, the wavelength will get shorter, the frequency will stay the same, but there's going to be a bending of the wave. And I know that's a little bit hard to visualize sometimes. Why do the waves bend when they go through from one medium to another? Now, one thing that's really important is that the wave wouldn't bend unless it struck the surface at an angle. So that is to say that if the wave came like this, we already looked at that in the last video. We looked at that with the soldiers. They don't change direction, they just slow down and you see changes to their wavelength. But in this case, what we want is a wave coming in at a pretty sharp angle. So I'm going to have this wave come in fairly sharply. So there's our ray. And when we're applying Snell's Law is set up to make measurements of the angle. You might think that this is the angle that we'd want to look at. But no, that's not the angle that we're going to look at. The angle that we're going to look at is going to be the angle with this line. And this line has a name in physics. It's a really unusual use of this word. I don't think I've ever seen anyone ever use the word in the same way that we're going to use it. The word is normal. And normal means perpendicular. So this line is perpendicular to the surface. And we are going to measure our angle, theta, with the normal line. So what I would say is that the light struck the surface at some angle normal to the surface. Normal to the surface means perpendicular to the surface. So the angle that I am measuring, the reference is with respect to this imaginary perpendicular line that goes through the surface. Okay, now obviously in this medium there is some index of refraction. So I'm going to call that N1, since this I called theta 1. This is the ray of light before it went into the new medium. So there's some angle that it came in at, and it's traveling in some medium that has some index of refraction. I'm going to call that N1. Now let's think about what happens when the wave transitions. So in order to do that, it would be really helpful to not have a skinny line. So you could use your pen, and this is what I would recommend that you do in the future, is that you'll use your pen because your pen has width. It has a left side and it has a right side as your pen travels along the path that the ray is traveling. But for our purposes today, let me use something that's even a little bit wider so that you can imagine this a little bit more clearly. So this blue ruler, let's imagine that this is the ray of light. Okay, so the ray of light comes in, I'm following this portion right here, and then right here at this moment, okay, I'm going to freeze the ray in place for just a moment. Let's think about what's happening. The left side of the ray, remember the ray's traveling in this direction, ray's traveling this way. If I look at the left side of this ray as it's traveling, its left side, not my left side, its left side, I would see that the entire left side is still in the fast medium. So the left side of this wave is still traveling very fast. But let's look at what's happening on the right side of the wave. The right side of the wave is actually already in the slower medium. So that means that the right side of the wave is going to slow down. So if you imagine the wave coming in like this, if I slow this part down, but I allow this part to travel just as fast, you're going to see that it's going to bend, and the wave is now going to travel in a slightly different direction. And which way is it going to be bent? If I go from the fast medium into the slow medium, then what's going to happen is it's going to bend towards the normal. It's going to be bent towards the normal because the right side of the wave is going to slow down as the left side is still going faster until the entire thing gets in. Now, once the entire wave gets in there, now everybody's in the slow medium and it will stop changing directions. But while the transition is occurring, you're going to see that the wave is going to change the direction of its travel and it will be bent towards the normal. So I'm really exaggerating this so that you can see it very clearly. And you will see that the new angle with the normal is a smaller angle. This is a smaller angle. On the other hand, of course, the new medium has an index of refraction. And just think about this. This is a really important thing to recognize about the index of refraction. This will be a bigger number than this one. Let me bring back the paper that we were looking at just a moment ago. As I went from very low density substances like a vacuum up to more and more and more dense things, my index of refraction is getting bigger. So my index of refraction gets larger when the speed slows down. There's an inverse relationship between the index of refraction and the speed that the wave will travel in the new medium. They follow a simple inverse relationship. So when the speed gets slower, the index of refraction gets larger. So let's take a look at what happened in this situation. I have an index of refraction that's small because I'm in the fast medium, but I have a very large angle. Now, when I transition, the angle gets smaller because the index of refraction is larger. This thing will have a larger index of refraction. Now, I'm not going to go through the mathematical proof. It's not super complicated, but for the purposes of what we need to do in this class, I don't need to go over the proof for you. It is in the book, and also you can find it online. Why does the object bend like that? What's the mathematical reasoning behind it? But I am going to simply give you the law, and that says that if I multiply the index of refraction, not by the angle, but by the sine of the angle. And if you just think about why am I using the sine of the angle has to do with the fact that look at the gap between here and the wave, and look at the gap down here between here and the wave. Much bigger gap here, much smaller gap here. Okay, so the sine of the angle would be looking at this opposite side. Imagine we made this into a little triangle. It would compare this length, the sine of the angle would allow me to compare this length to this length, and you can see they are dramatically changing. So if I take the product of the index of refraction and the sine of the angle, that must stay constant all the time. When I multiply those two things together, I will always get the same number. If the index of refraction is larger, then I will see that it will bend even more. If the index of refraction is slightly lower, then I'll see that it won't bend quite so much. What would happen if I went in the other direction? What if I was traveling this way? Well, let's bring back the ruler and let's see what would happen. If I travel in this direction, what I would see is that as I transition, I would see that the right side of the wave would hit the fast medium. That means that this part of the wave is going to begin to speed up, while meanwhile this side of the wave is still traveling very slowly. So as this guy travels slow and this guy travels fast, you're going to see that it bends the wave so that the wave is traveling exactly like our picture. I could actually take these arrowheads and flip them around and it would still be the exact same picture. There would be no difference at all. The wave going from the slow medium into the faster medium will turn away from the normal, whereas going from the fast medium into the slower medium, I will turn towards the normal. Okay, and don't forget that N is equal to C over Vm. Okay, so let's take a quick look at an example problem. Let's look at a very simple problem. Just for the record though, there are 4 variables in here. You could be asked to solve for any variable. I could give you the 2 indexes of refraction and tell you the angle of the incoming ray and ask you for this one, and that's what we're going to do in this example problem. Or I could give you both of the angles. I mean, look, this is something I could easily measure. Let's say I took a laser light and I shined it into a tank of water. I could take my protractor out and measure this angle. I could measure this angle. I know that in air, the index of refraction is basically 1. It's almost exactly the same thing as it would be in a vacuum. And that would allow me to calculate the index of refraction. And that's kind of an important thing because this equation would be very difficult for me to measure the speed of light. If I already knew the index of refraction, of course I could use it. But actually measuring the speed of light in a new medium, that's a really difficult thing to do. So if I use these angles to calculate the index of refraction, I can then go to this equation and plug in the index of refraction and the speed of light in a vacuum, and I can calculate what is the speed of light in this new medium. You can calculate using this technique by using nothing more than protractor and your calculator. You can work out the speed of light. Remember, the speed of light, even in glass, is almost 200 million meters per second. Almost 200 million meters per second, or about 120,000 miles per second. Obviously, how would you do that? What kind of equipment could you use? It would be very difficult. But Snell's law allows us to measure the speed by combining these 2 equations together. I can use the information in the angles combined with the incoming index of refraction to work out what the new index of refraction is. And once I have that index of refraction, I can use that then to calculate the speed of light in the new medium. So let's take a look at a quick example and how will it play out. I'm going to read carefully through the problem, as I would expect you to do for all of these problems, and think about what is theta 1 and n1, and what is theta 2 and what is n2. So this question says that a ray of light traveling in air, that's my 1, that's where it's starting in the air, and then it strikes a pane of glass. That is my second object. Okay, so I have the 2 things. I have the ray of light was in the air, it struck the glass, it was transmitted into the glass, and the question is, what is the angle of the path that it travels through the glass? Now what I am given is that the pane of glass has an index of refraction of 1.54, and that the angle that it came in when it was in the air was at 58 degrees. This is not the angle in the glass, this is the angle in the air. This is the angle that it struck the glass with, but it doesn't tell you anything about what happened once it struck the glass. So what I would recommend is, just in order to keep everything really straight and very clear in your mind, when you write out what is given to you, I would make sure you identify what are the 2 mediums. So in this case, air, which has an index of refraction of 1.01, and it has a theta, that's N1 and theta 1. The theta is 58 degrees. Okay, in the glass, N2, we were told that the index of refraction is 1.54, and what I'm looking for is this angle. I want to know what is the angle that the light traveled through when it went through the glass. Okay, so Snell's law says that N1 sine theta 1 is equal to N2 sine theta 2. The product of the index of refraction and the sine of the angle must always give a constant value no matter what. Now, what I would recommend is I would just go ahead and plug the numbers in. Okay, you can do the algebra if you want to. There's nothing wrong with it. That's a fairly sophisticated way of solving the problem, but you can solve the problem without having to go through the algebra first. It will simplify the algebra because you'll see there's a lot less algebra to do if we do some of the math first, and then we worry about the algebra with moving things around. So I'm just going to go ahead and plug in everything. 1.001 times the sine of 58 degrees must be equal to 1.54 times the sine of theta 2. Okay, now obviously 1.001 times the sine of 58 is not really going to change the sine of 58 very much, but let's take a look at how that calculation is going to work out. So let me bring out my calculator. I'm going to take 1.001 times the sine of 58, enter. Okay, so on the left side of my equation, I have 0.848896, but I'm going to go ahead and do a little bit of algebra right now. Let's go ahead and make two steps. So let me go ahead and do this multiplication, and then also let me divide by 1.54 to move this over and detach this from the sine of theta. So right now I'm just going to say divided by 1.54. That is equal to 0.55123. Okay, so now this is an important step, and it's something that some of you may not have a lot of experience with doing, and so this is something that's really going to take some practice. It's something you really want to think about every day to really get this skill down. How do you get the angle back? So I'm not giving you the angle. If I gave you the angle, you would just say sine of the angle, and you would hit enter. But now what I want is I want the angle to come out of here. So I need to undo the sine. And the way that you undo the sine is by doing the inverse sine. So that is to say that the inverse sine of the sine of theta is just equal to theta. These two things undo each other in the same way that 1/2 times 2 theta would also be equal to theta. 1/2 is the inverse of 2. So these mathematical operations cancel each other out in the same way that the inverse sine also undoes the sine of the angle. So on the right side, what I need to do is take the inverse sine of the sine of theta, and that will leave me with just theta, which is what I'm looking for. But that means I also need to do the same thing on the other side. So on your calculator, when you look at the sine button, you should see right above it, it's going to say sine to the -1 power. That's what I need. So inverse sine, and now I'll put in that number, 0.55123, hit enter, and there is my angle. So in this case, it turns out to be 33 and I'm going to call that 33.5 degrees. And that is the angle of the light ray as it travels through the glass, the path that it takes. Now, I could have asked you to solve for the index of refraction of the incoming light, or I could have asked you for the index of refraction for the light that's traveling through the new medium. I could measure the angle in here. I can measure the angle here and give you the 2 index fraction and ask you, well, what was the incoming angle? What angle did it strike the new medium at? So any one of these 4 properties can be solved for. I don't want to give you the impression that the index of refraction is only for solving for the angle of the refracted ray. It's not what it's about. I can solve for any one of these 4 properties equally well. Now, before we end the video, let me just show you like a really interesting aspect about this. There's something really important about the way light behaves, and I'm going to look at the reverse path of this. I'm going to look at the path of light traveling from water into the air, and this is maybe going to seem a little strange, but we are going to actually imagine that we are all bears. And bears love fish. They like to catch fish from the rivers and from lakes. And so let's take a look at what does it look like to a bear when they look at a fish in the water. And you're going to see that the refraction is actually really significant. It plays a really significant role. And bears, they learn how to deal with this. They know what to do in order to be able to catch the fish, even though the light that is showing them where the fish is going to be refracted. So this is air, and this is water. We're going to put a little fish. I don't want the fish to be too close to the shore. I want it to be out here just a little bit. So I'm going to draw a little small fish. So a treat for the bear. I'm going to attempt to draw the bear. I'm certainly not a great artist, so I apologize in advance for how terrible this picture is going to be. But I really only need the head of the bear. Okay, so here is our bear. Okay, so the bear has eyes, right? And the eyes are what allow you to see the fish. Now, one thing you should really think about is, how do you see things? You know, your eyes don't reach out to see things. They only just passively sit by, and they just allow whatever light happens to strike them. They absorb it. If no light comes to you from an object, then you will not be able to see that object. So light comes into the water from above. It goes down into the water. It gets refracted when it goes down into the water, but I don't want to look at that refraction. What I want to look at is the refraction when it leaves the water. So light comes in. It strikes the things inside the water. That's how the bear can see the fish. And so let's imagine the light ray. I'm going to use this ruler for just a moment. Let's imagine the light ray that would travel from the fish, bounce off the fish, and then travel straight towards the bear's eye. So I'm going to draw an arrow. Okay, but then I'm going to stop it right here. Okay, but because the reality is that ray of light is not going to travel to the eye of the bear. It was going to travel to the eye of the bear, and if the bear was underwater, that ray of light would have traveled right directly to the bear's eye. But remember, when the ray goes from the slow medium, which is the water, to the fast medium, it turns away from the normal. The normal is an imaginary line here. I'm not going to draw it because I don't want to clutter the picture too much. There's an imaginary line here, and the rays of light, when they go from a slow medium like water into a fast medium like air, they turn away from the normal. So the ray of light that the bear is looking at right here, this ray of light is going to travel something like this, and it's going to hit the bear right in the chest, and the bear will not see that ray of light. So then what ray of light does the bear see? Well, the ray of light that the bear sees is the ray of light that goes like this. This ray of light goes up at a little steeper angle, doesn't hit this quite so sharply, and then it also refracts, not quite as much as the other one did, but it also refracts. And that ray of light will travel to the bear. Okay, now, a really important thing to understand about how you see things is that your experience throughout your entire life, as with every living organism on Earth that can see light, have all learned that light travels in a straight line. So if you see light coming from this direction and striking your eyes, well, that would tell you that that object must be along this path. That means that for the bear, the fish looks like it's over here. So, and this phenomena is super easy. I'm sure you've seen it before, and I'm actually going to give you a way of you to test it out yourself. The bear, when it looks like the fish is over here, a little farther from the shore than it is. But the bears know, because they've had experience to realize that when they reach into things that are in the water, they're never where they look like they are. They are always closer to you than they appear to be. They are always closer, because the light that's going to travel to your eyes is going to bend in such a way that makes it appear as though it's actually along a path that is farther away. Now, I would encourage you to please test this out. You could use a bathtub. That requires quite a lot of water. I would suggest that the best thing that you could do is use your sink. Now, you can fill your sink, I would say, don't necessarily fill it all the way up, but I would fill it up pretty close to completely full. An empty sink. Block the bottom, put a stopper in there, fill that sink with water. Okay, take something very bright, dense that will sit down at the bottom of your sink. And what I would like you to do is, don't look directly over it. So first of all, if you look directly over the object, it will actually appear exactly where it is, because there won't be any bending. right? The light doesn't bend unless it strikes the new medium at an angle. And in this case, the medium is water and then going to the air. So what I want you to do is take your finger, once you're ready to do that, you've dropped your object down into the sink, step back a little bit so you can still see it, but you're not directly over it. Take your finger and move directly towards the object, and you will see that you always go farther away. As soon as your hand gets in the water, you're going to realize, oh, your hand's not heading towards it. That's not where it really is. It really isn't at that point. And you're going to see that the object is actually closer to you than it appeared to be when you looked at it with your eyes. And that's because of the refraction of the light traveling through here. Please make sure you do that. I'm sure you've seen examples of, people oftentimes take a glass of water and they'll put a pen in there and you'll see the pen looks like it's a little detached. That's a good example of refraction. But a better example is test it for yourself. Everyone who fishes in the water or who tries to get something out of the water, they know this. They know to reach to a point which is actually closer than where it appears to be if they want to get it. And as soon as your hand gets into the water, you'll see that your hand's not going to the right place, and then you can adjust and you can move your hand to where it is and put your hand in there, and what you'll most likely see is that it's going to look like your arm is bent. Your arm will